Hello everyone and welcome to lecture. In this lecture I'd like to talk about the final topic that I want to talk about from chapter 1. This is material that is in the notes that I'll post when I post this lecture. The main idea here is that this is, so in the notes, in that note file that I'll post when I post this lecture, this is in the third section of that note file. The note file basically goes over propositional logic in the first section, predicate logic in the second section, and then the topic that I'll be discussing today, or in this lecture, which is the topic of axiomatic systems. And basically, in some sense, we can think of any mathematical theory as being inside a certain axiomatic system, it being inside some axiomatic system. So we say that an axiomatic system is exactly a finite sequence of propositions, A1 to AN, which are called the axioms of the system. So the idea here is that any axiomatic system has to be what's called consistent, and we'll define that in a little bit. But we're going to see that there are certain things that have to be true when you're working inside any given axiomatic system. And if you watched the previous lecture on introduction to proofs, you should have seen a number of different examples on how to prove something using many different ways. What we're going to do right now is put an actual definition down for what it means to prove a statement within some axiomatic system. We do this as follows. We define a proof of a proposition P within an axiomatic system. So inside some relative to some axiomatic system is a different finite sequence of propositions. And we'll call the finite sequence Q1 to Q2. So we'll do Q1, Q2, Q3, and so on and so forth, all the way to Qn. So it's a finite sequence, and I already used n up there, so we'll use m, such that the last thing in the sequence, Qm, is itself P. So Qm is our conclusion P, and for any one of the J, so any one of the propositions in our proof, or in our sequence of propositions, satisfies the following three, or one of the following three things. So we have to have that Qm equals P, and for every argument or any value of J from 1 to M, we have that one of the following three things are satisfied. The first thing is that Qj is a proposition from the list of axioms in our axiomatic system. So Qj is really equal to one of the axioms in our list of axioms. T is the second thing that we have here. So either each one of these things is an axiom in our proof. Each one of the things is a tautology. We talked about that before. Qj is a tautology. Or remember from before, this just means that Qj is, so it's the same thing as saying Qj is a valid rule of inference. So this is the second possibility. A proof contains a sequence of arguments such that the arguments can be axioms, they can be valid rules of inference or valid tautologies, or we have the last remark, which is that there exists two previous propositions. So there exists two M and N that are between 1 and J, so two previous propositions such that the implication such that Qm being true and Qn being true imply Qj being true. So this is the basis for a proof. This is the definition of what it means to prove something. A proof is just a sequence of propositions such that either we're taking up something from our list of axioms, either one of these things is a valid rule of inference, so it's a tautology, and then lastly we could have we could also have that Qj, or any one of these things, could depend on two previous entries in our list of steps in our proof, So the idea here is that these steps and this definition of proof allow us to very easily recognize a proof and check a proof and check whether it's correct or not. The idea is that we want to be able to sort of be able to very easily check whether a given sequence of arguments is a proof or not. And the idea is finding a sequence that's a correct sequence is something that can be checked by a computer. So there are what are called automated proving systems or automated theorem proving systems that essentially allow you to check whether your sequence of logical steps in the process of proving something is correct and validate that your logic is correct. It's very, very cool. It's a neat idea. But just a little remark here that sometimes we say that if a statement P can be proved within an axiomatic system, we sometimes write that as A1, A2, AN, and then we put, it's this symbol right here, P. It's more directly, if you were to write this in terms of a statement, it's the statement that statement P can be proven in the axiomatic system A1 to AN. So this is kind of a neat idea, and I guess you might want to ask, well, what constitutes an axiomatic system? What is an axiomatic system? Well, what's the simplest example? And really, the simplest example that you can have of an axiomatic system, as the most extreme case, is propositional logic itself. So, like, I guess our first example of an axiomatic system is itself propositional logic. This is the axiomatic system where we take the empty sequence, or the sequence containing no axioms, as our set of axioms. And what that means is that the only thing that we can prove in propositional logic, so the only, and we've seen this already, but are tautologies. Using this definition of a proof right here. This is the only thing that it's possible to prove in propositional logic. So I guess for any, if we want to do more complicated mathematics, we have to add axioms, more and more axioms to our axiomatic system. But this is kind of a neat example, a very neat example. Another example of an axiomatic system is set theory. So this is kind of where we're moving towards. It's one of the first big theories that we have to first kind of get down and understand a little bit about. Set theory is the theory that you get when you make a certain number of axioms. There are different forms, or I guess different types of set theory. And depending on the axioms that you take, your actual theory will be different, and the properties in that theory will be different. So you have to be very careful. But typically, set theory consists of what are called, the 9 standard, sometimes called ZFC axioms. So I'm not going to be talking about these anymore in this lecture, but in the next few lectures, we'll be talking about how to construct what's called Zermelo-Fraenkel set theory, or ZFC set theory, which is essentially constructed through these 9 standard ZFC axioms that have been very well kind of understood and developed. And they didn't become developed at once. I'll give more on the history when we go over the actual set theory itself. But the idea is that these set theory axioms have been developed as the correct axioms through a very long time, many minds thinking about how to correctly construct the axioms for set theory. There's a reason for each individual axiom, and we'll see why when we go through and start using set theory. But so what I want to do and how I want to what I want to talk about for the rest of the lecture really is what we need an axiomatic system to contain. What it's necessary that an axiomatic system, or if there's any necessary properties that an axiomatic system has to hold. And it turns out there is. It's what's called consistency. It has to be a consistent axiomatic system. So first, I'll define what that means. We say that an axiomatic system is consistent so an axiomatic system, we sort of A1, A2, AN. Remember, this means we have a number of different axioms that form our axiomatic system. It's consistent if there exists a proposition Q which cannot be proven from the axioms. So in symbols, what this is saying is that there exists a Q such that the negation of A1 to AN can prove Q. So this is saying that there exists some Q such that we cannot prove Q inside the axiomatic system with axioms from A1 to AN. So this definition may seem arbitrary at first. Like why would we want to define consistency with this logical statement right here? And it turns out there's a really good reason why this is in fact the definition of consistency. This has to be the definition of a consistent axiomatic system because of the following reason. So let's consider what we're going to call an inconsistent axiomatic system. That's an axiomatic system which contains contradicting propositions. So we have here A1 is one axiom, A2 is another axiom. Say we keep going until we get to some proposition S in our list of axioms, and we have, let's say, a contradictory assumption. So we also have maybe not S in our list of axioms, and all the way to AN. So let's just assume that we have an inconsistent system. Our axiomatic system is inconsistent. Or you could say contradictory. If this is the case, then there's going to be two axioms which contradict themselves in our axiomatic system. So if this is the case, then the idea here is the following. Then given any proposition Q, it doesn't matter how ridiculous Q is, but given any proposition Q. And I'm up here in important. This is no matter how ridiculous. We can prove Q in a contradictory axiomatic system. And you could ask yourself, how is that possible? Well, it's possible because of our base definition of proof and our base definition of the implication operator. The proof of any proposition Q can be written as S and not S implies Q. And the reason that this is a valid proof of any proposition Q is because this is a tautology. And this is a tautology because this proposition, this S and not S, is always evaluates to false, which means the implication S and not S, so if S and not S, then Q, will always evaluate to true because we're starting with a false statement. So the main idea here is that, I guess this shows that any proposition can be proven, no matter how ridiculous or how false that proposition is, but any proposition can be proven within an inconsistent or we'll put here inconsistent. A synonym for that is contradictory. So proven within an inconsistent axiomatic system. And what that means is that we must define a consistent axiomatic system as one that has the negation of this property. In the negation of this property, the negation of any proposition being able to be proven within an axiomatic system is exactly this statement, or where did it go? It's the statement right here. This statement right here. Because what we've shown is that in inconsistent or contradictory axiomatic system, we can prove anything. We have that for all Q, A1 to AN, within this axiomatic system, we can prove the statement Q. So in an axiomatic system with this property, we have contradictions in our axioms. So what we must do is take the negation of that and make sure that any consistent axiomatic system, so any consistent or non-contradictory non-contradictory axiomatic system must have the negation of this property, or must satisfy the negation of the statement for all Q A1 to AN, or Q can be proven in the axiomatic system A1 to AN, in the negation of this statement is exactly the statement that there exists Q such that the negation of A1 to AN Q, which is the statement that there exists a proposition who cannot be proven within our axiomatic system. This is why we have to define in a consistent axiomatic system like this. And it's very, very important to do this last step, one last step, kind of showing an example of this, to show that everything that we've been doing is in fact a part of a consistent axiomatic system. So this is a huge piece of importance here. We have to have the following theorem. We have to be able to show that propositional logic itself is consistent. Propositional logic itself is a consistent axiomatic system. And we can do this. There's a number of different ways of doing this, but the main idea here is the following. Right? We have to show that there exists a proposition. We need to show that there exists a proposition Q which cannot be proven within propositional logic. So we need to find a proposition that cannot be proven within propositional logic. And that will, if we can do that, then that will show that the propositional logic is a consistent axiomatic system. So we need to find a proposition Q which cannot be proven within propositional logic. And what you want to remember is that this is, in some sense, relatively straightforward to do, because the only thing that we can prove in propositional logic is tautologies. We mentioned before that within propositional logic there are no axioms. We don't have any list of axioms, so any proof in propositional logic will not rely on the axioms, because we don't have any axioms in propositional logic. So we really only have T and M as being relevant in this proof. And the point here is that T only allows the insertion of a tautology. QJ here can only be tautologies. It can't be any axioms, because we don't have any axioms in propositional logic. So really the only two things that we have here, the only two options that we have here, are T and M. So I'll copy this over so we just remember that we don't have any axioms in propositional logic. We only have the possibility of taking tautologies and doing implications with the various tautologies. This is what we have from propositional logic. We'll take that, copy it, and then paste it right here. These are the only two scenarios that we can have here. And what's important when we realize this now is that if we can only take tautology, so QM and QN to be tautologies, or insert tautologies into this implication, then that means that in order for an implication to be true, any QJ that we come up with must also be a tautology. So any proof sequence that we construct is always going to consist entirely of tautologies, and thus this is the important result right here, that so for any two QM and QN, say if we do Qn and Qm imply Qj, well, because Qm has to be a tautology and Qn has to be a tautology, right? Then the only way this implication is going to be true is if Qj is itself also a tautology. So really, any proof in propositional logic consists only of tautologies. Not only that, but furthermore, the only statements that can be proven in propositional logic are tautologies. And this is the big thing about this proof. If we can only prove tautologies in propositional logic, that means that any contradiction we write down is not a tautology, and thus it can't be proven. Or is a statement that can't be proven within propositional logic. So write down your favorite contradiction. I'll write down the statement. If Q is a statement, we can call S the statement. So define S as the statement Q and not Q. This statement is a contradiction and thus cannot be proven within propositional logic. And there we are. We're done with the proof of consistency of propositional logic. So this is a big result, and it allows us to essentially base any and all mathematics that we do off of propositional logic. And it's also a very important thing in terms of this actually is exactly extremely related to what's called the Gödel's incompleteness theorem. And I'm not going to go over exactly what this says, but it essentially is saying the results of this consistency. It has to do with consistency of an axiomatic system. And it says that there will always be something that you won't be able to prove inside the axiomatic system that you're working in, which is something that at first was viewed as a very negative thing in mathematics, but as time has gone on, it's actually a very positive thing in the sense that it allows us to be exact with what we're proving and what we're trying to show in a given axiomatic system. And it allows us to continually kind of improve and look for different versions, different axiomatic systems that work better in certain scenarios and whatnot. This is where I want to end today's lecture on what it means to be a consistent axiomatic system, and I hope that sort of clarified things for you, maybe clarified some things that may have confused you during reading or while you were generally reading mathematics papers and whatnot. But this is it for our propositional logic. We'll be moving into the theory of sets, so set theory and how to work with set theory and properly define set theory in the next couple lectures. That will conclude today's lecture. Thank you very much for listening, and I hope you learned something and had a great day.